some static types. That'll be nice. And in my spare time, I spend way too much time on making little games and websites. My favorite little project is Familiar.io, which is a sort of a MMO Pokemon clone, and the back end is built in Rust, and it is cool. Yeah, I don't know. I want a reason to get into Zig. It seems nice.
I'm going to give you a reason tonight. I'm going to do it. It might not be a good reason. You might not like it. It may not be convincing. I'm going to give you a reason.
Sounds good. Then I will look and I will learn.
All right.
Yeah.
I'm Andrew Gossage. I am the director of software engineering at a company called Gen AI Learning Solutions. We do grading automation, and I work primarily there. It doesn't leave me with a lot of free time, but our tech stack there uses JavaScript, Python, and Zig.
Cool.
I'm Sam. I'm just first time. I like a lot of different things. I think my biggest interest is like automation, scripting, Linux stuff, that kind of thing. But I kind of like touching on everything a little bit. My interest in low level stuff is probably just mostly to get to know computer science, kind of at an intimate level. And I eventually want to turn these interests into something monetizable, but right now I'm just doing what I can. And that's about it for me.
I'm Matt Madsen. I'm his son. I'm only here for the
And to wear the hat. You did come specifically to wear the hat. That's what I was told. So please don't downplay your role.
I don't have much coding experience other than Scratch, but
That's okay.
Scratch is legit. You can make real stuff in Scratch. It's good. That
Somebody
counts.
built a Linux deployment in Scratch.
Jeez, dude. Oh my gosh.
That's what we need.
Imagine.
Alfie?
So, yeah, I'm Alfie Madsen, and my preferred languages are Common Lisp, Forth, and Jane. But since it's kind of hard to find meetups for those things, I tend to go to Rust and in this case Zig, but occasionally go on Python as well.
If you start a fourth meetup, I will come to it.
If it doesn't conflict with the Zig meetup, I might come. Just
Okay.
because it's cool.
Yeah.
Since you like Common Lisp, you said Common Lisp, right? Are you an Emacs guy? Which is Emacs Lisp, but
I'm actually more of a Vim person. I did use Emacs for about a year and kind of respected it, but it never really gelled with me. And sometime after that, I saw a video about Vim and Vim motions, and I tried it out and have gone with it since then. Well, I have tried it at Evil a couple of times, but one of the tricky things about Vim is that they have a lot of interesting plugins that aren't really available to the emulators.
do you use regular Vim or NeoVim?
I use regular Vim, and part of it is because I'm kind of a little afraid of doing the dot file conversion from Vim to NeoVim.
Yeah, I've wanted to do that.
Are you writing in Vim script then?
Well, my config file is fairly basic for this script, so
Oh yeah, sure.
I would have to go
Plug it
through
in for you.
and check for plugins and make sure things are working.
Lua is really easy, so.
You can also use Vim, the older versions of Vim fit in NeoVim, not the newer ones.
I'm Robert. I'm a fiber technician and coding. I'm most interested in like game dev stuff, but I'm kind of into everything.
Ulysses. I've been doing Go for a while now. That's kind of what I love to do. But I love home lab, embedded systems, microcontrollers. So I'm excited for this. And I've been wanting to come here for a while to learn more about Zig. I've heard a lot about it, but I haven't had time to check it out. So I'm excited to be here. I'm Stephen Brown. I'm new to computer science. I've been self-studying and for the last 2 years done the Dead Mountain Boot Camp. Did that last year. Doing a back-end development course called Boot.dev. I don't know how many of you are familiar with that, but anyways, I'm interested in learning more about lower-level programming, and I'm also really interested in microcontrollers. So.
Cool.
Hi, well, my name is Niall Salter. I've given a few talks on this channel, and Zig is my religion. It's my main language that I love. I agree with everything that Andrew Kelly says, pretty much, and yeah, anything else is blasphemy generally. So
That's good.
I'm finishing up the compression-based tokenizer I presented on last October. I'm finishing it this week.
Oh, yeah,
So
that was cool.
Well, thank goodness we have at least one voice of reason at the table. Oh, the rest of us heathens. All right, so let me see if I can get this in here. I'll switch over. Okay, so and now we'll remove the time countdown thing. All right, so big thanks to Vivint for hosting us, for providing the pizza. Thanks to Jeff, who was hanging out there because I must have scared him off at some point. But for making sure that things are taken care of so we can get scheduled, we can have that food. Want to just acknowledge and appreciate them for that. Welcome to Utah Zig. To those of you online, like, sub, follow if you want to. But remember, this is not a good Zig channel, so don't get your hopes up. And for the rest of you, same thing. I do not know hardly anything about microcontrollers. It's always been frustrating for me. And so I thank you for coming. I will do the best that I can to give you the education I have, but most of my time, since I announced this as being what I was going to do, has just been me trying to learn and figure out what the pieces are. So it's not really much about Zig, but I do have some arguments as to why I think Zig is maybe a solution to the frustrations I felt. What were you going to say, Nels?
I actually, someone messaged me on LinkedIn asking if our channel was affiliated with a university.
Interesting.
That was kind of a funny mistake to make.
Utah. Affiliated with like Utah.
Yeah.
Utah, University of Utah channel?
Are we out competing then?
Okay, so I have up here a picture of Angelica. Some of you are children of the 90s or thereabouts.
Just so you know, the camera can't see the thing if you care about that.
The camera can't see what thing?
I think
You can
he's
see
screen
about half
sharing.
the TV.
No, this is being recorded
Oh, okay.
separate. So it's, if you want to see what my setup looks like, this is what it looks like.
Okay, cool.
Okay. So sorry, I'm not going to show everybody because if I turn it around, then one of the cables will come disconnected. And was it when you were presenting, the audio came disconnected, like something?
Yeah.
I'm so sorry about that. That stinks, but happens sometimes. Anyway, so the reason I've got Angelica up here is my favorite line from the Rugrats was the episode where Tommy or whoever it was goes and asks a question, and she says, "Well, if you have to ask, you'll never know." And there are some things that are like that. There are some things that are guarded secrets that you're in the in crowd or you're not in the in crowd, and there's no way to cross the bridge. Like, you work with the tools that you're given, or you know how to create the tools, but there's no documentation, there's no bridge, there's just not a lot of good resources for when you don't know what the words are that you don't know, to even figure out what the words are that you don't know. And then when you go to ask somebody, you're like, "Hey, I'm trying to figure this out." They're like, "Oh, MicroPython, bro." And you're like, that doesn't help. Okay, so that brings me into the next point. So I got some talking points here, and then we've got a little demo. So one of my frustrations in approaching microcontrollers is it seems to be predominantly what you're buying is toys for kids. You are not, if there's somewhere to find professional level material, please let me know where it is. But it's like, there's some hobbyists with like audio that sounds like they're across the room in another neighborhood or something. And the static, there's like not a lot of good resources. And the things that they have good resources for, it's because they're selling toys for kids. There's the Arduino, whatever, and then they get rid of it. I go, "Oh yeah, you should start with Arduino. You'll just never put it in production. There's no way to deploy it, or there's no way to package it up easily." It's like, okay, well, you just sold me on why I would never want to start with Arduino. Why do I want to start with something where I'm not gonna really sink my teeth in and get it done. And then you have, the Raspberry Pi is becoming popular with. We got a funny comment in the chat there about the university affiliation and wanting to hear about your tokenizer. Anyway, so then we've got the Raspberry Pi, which I think that a lot of their stuff actually is production ready, but their answer for how do you develop on this thing again is you're going to use MicroPython or something. If you look into STM32, they have their own. Well, this is the next point. So the stuff that's easy and that's accessible is for kids. It's not for professionals. It's not for a product. It's like, here's how to tinker around and get the temperature of your soil for your, home garden and Rube Goldberg machine, which is cool, right? Like that's cool, but that's also not where I want to start. So I love the idea of microcontrollers and just been hesitant to get into them. I just don't want to because everything seems so far away, but that's the next point, is abstract all the things. So you go to the STM32 website and they have a complete IDE. They can't tell you, here's how to write code for this thing. It's like, well, here's an IDE and here's a plugin. Also recently, I just bought one of these. I'm really excited about it. I'm about 15 to 16 days away from my order shipping, according to an email that I got this morning, plus or minus 10% or something like that. But so this is using an ESP32. It's an e-ink screen. They have got, actually, it looks like an actual real plastic mold for the case. And what you're looking at here, they're selling it for, I think it was around $150.
Oh, not bad.
But, like the hardware, what does this thing cost? If you look at it from that perspective, it's well, you could look at it two ways. One, you could look at it, well, it's an IKEA frame that's $10, a $3 microcontroller, and a $7 e-ink display. Or you could look at it as it's $60,000 of development time and a $20,000 plastic mold. Well, hopefully not $20,000, maybe $7,000, $10,000, whatever it is, right? So you can look at that either way, and their real product actually is not the device. As far as I can tell, their product is actually a widget system. So this device, when I look at it from a market perspective and the way they treat the device, the way they talk about the device is actually to get community. What they're actually selling this appears to be a widget system, because they have guides on how to make your own device and how to contact through the API and all that. So it seems like the device is actually a loss leader to get the cool YouTube bros that are doing the cool stuff on there, which I think is great. I think that's wonderful. I hope that they go further than this device, though. I really hope their business isn't just the widget system, because it seems like you could do so much more if you started with something niche and then expanded out and really focused on users. So we'll see what happens. But anyway, but yeah. So if you want to go program for that, that's an ESP32. The ESP32 has Wi-Fi built in, and it's a proprietary Wi-Fi driver. You can get access to the header files and you can get the compiled code, but you don't get access to the source. It runs in a couple of different modes, one of which is a RISC mode. If I remember correctly, it's a type of processor that I'd never heard of called Extensa. And then I believe that it has a RISC mode.
RISC 5? Yeah,
RISC 5, sorry. Pardon my ignorant, blasphemous talk. But yes, RISC 5. Yes, because RISC is a ARM and RISC-V, et cetera, in there, and I do apologize for that mistake. Anyway, so with that, you've got the Wi-Fi and everything on there. But if you want to program for this device, there is a custom tool chain. So for those, I think everybody in the room knows what a tool chain is, but I will explain in the way that I know how. I'm not going to get this description perfect because I just know it anecdotally as the way I use it. But the tool chain is the set of core, compiler, linker, and built-ins like the standard C standard library. It's the built-in components that allow you to create a binary from source code. So you have source code, you use various aspects of a tool chain. The tool chain produces an executable that you can either double-click or run from the command line or flash to a device or some such. And that is your tool chain. So for the ESP32, you have to have a custom toolchain that is only provided by the Extensa company. And if you want to use it anywhere else, it has to be bundled and repackaged. And so then you get things like the newest thing is called Platform IO. This is the newest take on toys for kids, as I'm calling it, which I think Platform is trying to gear itself more towards enterprise. And I think they're trying to be like, instead of forking Eclipse, let us give you a VS Code plugin that will download your binaries from your website and then run the thing in VS Code. So I think that that's a huge step forward from having forks of Eclipse. Has anybody actually worked in Eclipse before? It's like this editor that's like Emacs, but for a GUI. It's like an operating system. It has more panels than you can possibly have monitors for, and it runs at about 1 minute hertz. So like, any operation you do, go get a coffee, come back, then do the next operation. That includes typing individual characters. It's like this thing for colleges and whatnot. But a lot of the pretty much every microcontroller toolchain I had looked at until Platform IO started doing their stuff was these forks of Eclipse, and it's a really heavy, sloggy editor. It was originally for Java. It was really popular in universities. But if you do microcontroller stuff, you'll find it again today. So we've got everything is abstracted in this thing. Like if you know, and if you don't, you don't, because they don't give you the documentation. Here's how to run the toolchain. The documentation they give you is install our 15 megabyte operating system fork of Eclipse, and then click the play button with the sample files and edit the sample files. Like they don't even give you here's how to start from main. Okay, so that's the next problem we got. And then as I'm trying to learn all this stuff, there's just missing pieces, things I don't know. And one of the things I found out turns out to be incredibly important, and I think is the reason for everything up to this point, is actually the linker script. Linker script, and I'll try to bring up the blog that I learned from that I found to be very valuable. I'll wait to do that though, because I don't have that link on hand. It's on my phone, and then I have to look through a message. But or Niles, if you could just send that one back to me. I think I sent you the link to the blog with the funny fonts that looked really cool, but it was actually really valuable information. If you happen to be able to do that real quick so it pops to the top, I'd appreciate it. So with linker scripts, basically it's a language that existed kind of before programming languages, if I understand it correctly. Like people were writing in assembly and they would use a linker script. And I've never understood what a linker is. I think, does anybody have experience with linkers here? Okay, you do? Yeah, okay. So anybody that's like deep into Rust or Zig, I think has experience with linkers. But essentially what the linker is doing, and I think this is pretty understandable, your function gets translated to assembly, and that function is basically, it's goto style, right? So there's something that loads some stuff into memory in a register in the CPU, so something that has maybe 32 bits or 64 bits or 128 bits, or I don't know how big it gets or how the SIMD stuff is counted for, but 512 bits. Yeah, the AVX. What is AVX?
512.
Yeah, what does AVX 512 mean again?
It means it has 64-byte vectors. It also includes like vector compression and expansion and a bunch more. It fills in the holes in like AVX and stuff.
Okay.
My computer supports it.
I have no doubt. So there's these registers that hold just a few bytes at a time on a CPU or a microcontroller. CPU microcontroller, kind of same thing, just one's lower power and doesn't have Windows on it, right?
I linked the thing in our latest message if you want to pull it up.
Thanks. I will pull that up. Let me finish my thought to get to the thing, and then I'll pull that up. So the linker script, basically what it's doing is it's saying, okay, we're gonna, whatever arguments the function takes, we're gonna copy from one place into another place as that function executes. So this is saying like this. Actually, I don't know if it already assumes that by the time you call the function, it's already been moved there. But it has the instructions, the assembly instructions. The assembly instructions say, move this memory from here to here, or use this address in here. Then run this sequence of steps on it, which are going to be lower level steps that are composed to create the things that we get to do in all of our high level languages like C and Zig, where high level is just not machine language in this case. And then once it goes through that set of steps, at the end, there's a go-to. Like anytime you have an if statement, one of the branches of that if statement is a jump, a go-to. And then it jumps to another place, and then eventually gets to the end. It says, okay, set some memory into some addresses into these registers, and then return. And then when it returns, it goes back to whatever it was doing before. That's your stack. And then it's likely that it sets some memory location on that stack so that it can continue with the result. Or it put it on the heap, which is just another place in the memory. Basically, I believe the stack, when you have your virtual memory structure in a normal program, I believe your stack starts on one end and your heap starts on another end, and there's some protections. If it's a kernel, at the kernel level, a lot of the microcontroller stuff applies. At the operating system layer, you don't really have to deal with any of this because it's all being virtualized by our operating system, and the program gets to start at its virtual address 0. But on the microcontroller, it's different. So what the linker does is it's moving things around and then providing relative addresses. So this function is so many instructions long, and it uses so many registers, and the linker is going to allow that to be compressed so that you need this function, you need this function, you need this function, you need this function. It's going to bring them all together, and then it's going to rewrite what the numbers were. So relative to itself in this library, the function started at address or line or instruction, whatever layer of abstraction you want to talk about it at. It started at 158. But when we compile this together and link it together, now instead of starting at 158, it becomes relocatable. It now starts at 5002, except it's probably a multiple of 4. Is that what is typical?
It depends on whether it's a 32 machine or 64, but yeah, typically you want to start at something that's aligned with the size of a cache line. So if it's 64 byte cache line, then you want 64 byte alignment when you start like a loop, for example.
Yeah. All right. So anyway, I'll bring up this post real quick so that I can reference it, because I would recommend that anybody read it. I don't understand it well enough to be able to explain it and provide a lot of value in that. I'm just giving a cursory overview, and then hopefully by the end of this, we'll show some DOS blinking lights. And I'll talk about the experience that I had with the microzig as well. We'll get up to that relatively shortly. Okay, come on.
It's like when we're using stuff in high-level languages, like libraries, for example, like libc, right? It's like there's a whole thing back in the day where it's like you could dynamically say, hey, I want to use the operating system is going to provide me this library to be able to do some addition or some special function, right? And then your linker would be like, yes, I'm going to statically link to that, which means that I'm going to take a copy and stick it here, and this is, or like you could also dynamically link it and say, hey, like I know that the operating system is going to tell me where this code is, right, somewhere. And so there's two different things. The benefits of statically linking is that all the stuff that you need to run your binary is there with it, right? Like the print, even like the print command, for example, right? We don't have to implement that, it's there. And that's part of the linker's job, right? Is at the end of the day, it's going to figure out, like, yes, all those references to all the things that it needs to know about that it doesn't know about the program, and it pulls all that stuff, like file, printing, whatever, and it's going to slot that in there.
I have a fun fact about linkers.
Yeah.
You will often hear people say that Grace Hopper invented the compiler, but she actually didn't. She invented the linker, but the first linker was named compiler.
Nice.
I think I heard that from you, actually. So.
I probably have said that before.
So this website right here, McYoung, XYZ, fun fact, XYZ are the #1 domain for spam and malware. So it's interesting to see one that's not spam or malware in the wild. But McYoung.xyz has this post only from 2021. So the last time that I dug into microcontrollers, this post was not available. And it gives the historical context, not just the technical detail, but the historical context. Like, context. Why is this file called this? Why is this file called that? He references different people that he talked to that were part of that era who, down in the footnotes, he says, I actually contacted so-and-so and asked, why is it named this? And he said, that so-and-so was doing this and named it that. So there's some of that in here. And for me, that was really important because you have names that clash, things that don't make sense. Like, for example, in the linker script is its own language, but it's not like a programming language that you would typically use today. It looks like something like a mix between BASIC and Haskell, if you can imagine that type of... I think there's probably an example in here, and we'll look at an example later. But it's very, very strange looking, and it is not intuitive in the least. But, okay, so here is one linker script, that's, or an overview, an abbreviation, it looks like. But .text is where your binary data goes, by convention. Because none of these actually mean anything except for if the toolchain dictates that it does. So, for example, the C standard library uses .text in some of the linker script data that it has. And so if you don't use .text, then when the linker goes to pull it together, it won't work right. And different microcontrollers have different conventions. Pretty much everybody uses .text for the binary file, which is just hilarious. But in terms of the other things, .bss is pretty standard. .data, .rodata, even there's variation. Like anything is up for grabs in the linker script. These are basically, forgive me for abbreviating too much, that they're basically address sections. So it's saying there's going to be an address and it's going to be text, and everything that's defined in the text section, it's just going to increment the counter for every item. And so what this is saying with the asterisks, this is a pattern matching. And what it's saying is that every section you find that ends in .text, that's named .text, so for example, you compile C code and it creates symbols. The symbols are going to end in .text or be part of a .text section. And so it's saying everything you find that's .text, pull that in. Canonically, it's supposed to be lexicographically sorted by symbol name, but that doesn't actually matter. That's just a convention as well. And then increment the address counter for every one. So it's going to pull in a function, increment the address counter. Pull in a function, increment the address counter. Pull in a function, increment the address counter. And then between sections, I think it's not between functions. I think it's more between sections, although maybe with some functions it does the byte alignment. But between sections, it almost always needs to be byte aligned. So if there's an extra 3 bytes in the text section, then it's just going to fill them up. It's just going to pad them out with zeros. And then it goes on. And this will fill out data with zeros. So when your program loads, all of the static memory that exists will be there. And in a microcontroller, your heap will also be there. It'll just be zeroed out. Actually, that's one of the first instructions. It won't necessarily be zeroed out. It'll be random. But one of the first instructions before it gets to the main function will be to zero out the heap. So there's that. Do I want to talk about board files right now? So yeah, actually this goes hand in hand. So like I was saying, every microcontroller is different in its conventions and its tool chain, except that .text is pretty common. But these are all arbitrary, and each board is going to have certain things that are special to it. So I talked about the stack and the heap and the application. When you're dealing with a board, there's another section that is called your vector table, your interrupt vector table. IRV, I think it is the name of it. And that section is where things that your microcontroller responds to, where their function handler needs to go. So in your program, typically you're not dealing with any of this interrupt stuff, but it's actually addresses. So you can mark something for the linker, and I don't have an example of this. I believe that there is one later on here. Maybe we can scroll to it. But in your linker script, you're basically going to tell it, hey, expect these sections to exist, and we're going to, it's in the initialization. The linker, I think, defines the section, but the initialization defines what it is. Oh, this is something else. I'm gonna jump back for just 1 second because this is one of the things that's completely unintuitive. What this means here, this is what I was talking about earlier. What this means here is it means there's a section that's called RAM that has an address. It's saying take this section data, copy it into the section called RAM, but do it relocated from the section that's called ROM. So when you load your program, it stores in ROM, your program, on the microcontroller. When the microcontroller initializes, it copies your program from ROM into RAM and then relocates the addresses relative to the RAM. That's something that you only find out from looking at a blog like this. I don't know where the documentation is, but probably in a GNU library anyway. But anyway, what I was saying is that you're going to have this vector table that has addresses to functions, and you're going to need to reference those symbols in your initialization before main. So there's actually code that runs. This is what it is. One of the initialization vectors is your init function for your program. So it's going to start the init function for your program, and the init function for your program is going to call main. So main is not called when your program loads. The initialization program is called, and your initialization program does things like make all of RAM zeros, like zero out your heap, set up your interrupt vectors. So tell the microcontroller based on its table, hey, when this button is pressed that triggers an interrupt on this GPIO, then this is the interrupt to handle that with. Or when you've got network traffic coming in, this is the interrupt to handle that with. Or if there's, I think it also covers things like seg faults. Is that right?
Yeah, I think what you're saying applies to actually all computers, and Zig does this by default. It will go into a start function before main, and you can write your own panic handler that will also use the interrupt vector addresses.
Okay. So hopefully, has anybody learned anything up to this point?
Yeah.
Okay, I'm glad that you've got. Oh, you put your hand up. I was going to say, I'm glad you don't have your hand up.
I mean, like that, and that's the thing way about thinking about interrupt handlers is just your keyboard. Like you push a key, right? There's something listening. All CPUs have interrupts, and that's how they do. But the operating system's kind of handling all that, right? It's just,
Yeah.
So yeah, like here we go. Like you receive the keyboard event, or you receive networking, right? And it's,
Yeah.
But in the microcontroller world, you're the one. Now you're in charge. You can say, oh, I want to listen to this event. So you put an interrupt handler and put a function there, and there's a whole fun slew of things that you want to do in interrupt functions that make them short, sweet, and simple. Because if you don't, you do some crazy stuff in your interrupt handler, you're gonna blow your machine up.
Yeah. So if you think about an event loop and like the way that Node works or Go works, or that async works in Rust, or that threading handlers work in C or Zig, then that's kind of what you're dealing with. Your interrupt is basically kind of your event loop handler function, where it's like, okay, I'm ready for a task, and you want it to be short and sweet and queuing up that task and doing whatever it does, which in a lot of cases is going to be set. I mean, this is where globals come from in C, like why are globals such a mess in C? Because when you have historically, when you have an interrupt handler, you need your interrupt handler to be short and sweet. So what do? You set a global, and then in your C code, the next time you come around to the while loop, the global is set. And this is also why in C code there's the keyword volatile, because when the compiler looks at your code, it doesn't necessarily know that it's going to go on a microcontroller. Your linker doesn't necessarily know it's on a microcontroller, because as Niles was saying, like all computers are this way. It's just when you're dealing with an operating system, all of that's abstracted away from you, and you don't have to worry about it when you're writing your program code. When you're on the microcontroller, you're writing the operating system. So, your program is the kernel. So yeah, you want to handle those things and be short and sweet about it, so that you set something somewhere, which unfortunately in a lot of cases you're going to take a shortcut and just set it to a global variable so that you can get it out of the way, so that the interrupt handler is done and you don't have to actually have it do whatever it's doing, but you have your main program, when it comes back around to its main loop of evaluating what needs to get done, it handles it. Or, if it's something critical, like in a real-time operating system, then you might actually want to halt the world and say, nope, the robot arm has to move over right now. It's the most important thing. Nothing else is important. And there's also priorities that you can set to interrupts. I don't know much about that yet, but I know that they exist. So, there's all that stuff. Okay, so next thing, yeah, talking about board files. So the board files, one other thing about that is they may have something special about them, depending on the microcontroller. So some microcontrollers are the common the von Neumann architecture, which is what our computers are, where instruction data and instructions and data are intermingled. And then some microcontrollers are von Neumann architecture, where in order for something to be a function, it has to be stored in a certain section of memory. And if it's data, it can't be stored there. So I don't think that you could write a JIT.
I think you said von Neumann twice. I think that the second one.
Harvard, sorry.
Yeah.
Harvard.
Yeah.
Harvard is where...
Yeah, I think that's right. Is it Harvard?
I forget which one's which.
Harvard
Harvard separates them.
Yeah, Harvard separates them.
Okay. So yeah, thank you for
got
that
it.
question.
Yeah,
Okay.
von Neumann is together, Harvard separates them.
Yeah, so Harvard architecture, because the other name for von Neumann is Princeton, but they didn't want it to sound too, Ivy League-ish. So
Yeah.
the other one, even though it's the Princeton architecture, is referred to as the von Neumann architecture, and the Harvard architecture is the one that failed. Well, it's just there's a lot of things about it that are clean but not practical, kind of like Rust,
Still alive in WebAssembly.
Okay, so yeah, and
Just like stack architectures. Also alive only in WebAssembly.
Yeah.
So there's a lot of things with your board file where you have to know specifically what the board is in order to set up the linker. The simple thing is, okay, where do instructions start? Where does RAM start? Where does ROM start? Those are the really simple things where you need to have addresses related to those things that end up being in your linker file. Because as you may know, every line on a CPU is, the lines on the CPU are the address. They get multiplexed, and if we want to talk to RAM is a certain multiplex input where you put a set of bits, and if the set of bits matches where the RAM goes, which is probably more of a bit mask, like all ones up to here and then zeros after, or zeros to here, then ones to here and zeros after. But if something is in that range of that bit mask, when the CPU goes out on the board, and zeros and ones are power or no power. So when an address is activated, that means that the power that's then going to load in those bits is going to a particular thing on the board that's done by physical traces that are on the board. And that's why you have these board files. And the reason, so the crux of the issue for me, the reason that I want to know about this stuff, why I don't want to use the kiddie toys like the MicroPython or whatever, is because I've programmed long enough, and even my brief stint in doing like 3 things with a microcontroller, I've programmed long enough to know that whatever the abstraction is, you have to learn the abstraction and the thing underneath, because when something breaks, and something will break, or when something's not implemented, and my very first job was dealing with something where if I'd known this stuff, maybe I could have solved the problem that we ended up outsourcing for. But it was, you have to know things about a board. Like a new microcontroller board version comes out. The RPi, there's the 2030 and now there's the 2350. And the 2350 is backwards compatible at some layer, maybe at the layer of the SDK or whatever, but it actually gets set up completely differently. And that was one of the hard lessons that I learned, because on the Raspberry Pi website, it said that the Pi Pico 2 is backwards compatible with the Pi Pico. And on the Zig website, well, not the Micro Zig website, but somebody answered me to a question I asked in one of the Micro Zig channels or forums or issues or whatever it was, and said the best supported thing is the Pi Pico. I was like, okay, I'm getting the Pi Pico 2. It's backward compatible with the Pi Pico. I'm going to load the Blinky. We're going to go. And that
Incorrect.
that was incorrect. And yeah, so anyway, yeah, so board files are a thing. They're all different. So I think that if you want to learn microcontrollers, if you just want to do the toy stuff, well, this is not don't listen to anything I have to say, because you can do the MicroPython with the Platform IO or the Eclipse editor, and you can do your little thermometer thing. But if you think me as what if you're a megalomaniac like me, and you think, oh, as one person, I'm going to make a difference in the world. I'm going to create some sort of microcontroller product that's going to sell to at least 10 people. Then, you should probably still go the microcontroller route. But if you're thinking like 100 people, Well, then, or sorry, I meant the MicroPython route. But if you're thinking 100 people, then maybe you actually need to know some of this information because you're going to run into a problem where you need to switch boards or use a new revision of the board or whatever. And so that's why I haven't been getting into microcontrollers, because I was missing this knowledge right here that it would allow me to have the vocabulary and what I need to say, okay, maybe when something isn't working, maybe I'll be able to fix it, probably not at this point, but at least talk with someone intelligently to be able to understand what the flip they're saying to me when they try to help me. And I'm not one of those people who's helpless. I'm just a little bit helpless. And then we're going to come around to microzig. So finally, we're going to talk about microzig. And at this point, I should have done this at the very beginning, but at this point, let me go ahead and show you some microzig. If I can get the box open and figure out which side I closed it on.
The other thing that with board files, like a lot of boards that you buy also have peripherals.
Oh, yes.
Kind of like, they might have different analog converters or, different communication protocol chips. And so basically the board files kind of have the drivers of the code that you need to interact with that other hardware on the board.
Yes, and so I was conflating terms earlier, so let me restate, because I was still kind of mostly talking about the linker setup. But yes, that is what the term board file actually refers to, and what I probably meant to transition to is yes. So you're going to have in your program code, like basically the kernel is a board file. or like the Linux, if you look in the Linux kernel, there's just directories and directories of board files for different things like the Raspberry Pi. And it defines, well, the Raspberry Pi has the hip bone connected to the knee bone, and the knee bone connected to the nose bone, and the nose bone connected to the eyeball, and so on and so forth, whatever way it needs to be. All right, so...
Sounds about accurate.
Yeah, that's about right. All right, so if I plug this in, everybody can see I have a device here. I got a light that blinks, and that is Zig.
Hey.
Wait, no, you can't applaud. You didn't show how it's done. I didn't do anything important yet. Well, I guess I shouldn't. Go ahead, applaud. Yeah. Can't tell people not to applaud you, because then you'll end up never being applauded when you want to be applauded. So I have to take what I can get. And then if I go over here, here's the other magical thing. If I touch this scary thing to this scary thing, watch what happens.
Oh, it stopped.
It's in reset mode.
Amazing.
That CPU's just going round and round and round doing a bunch of nothing right now. And look how fast it booted. Did you see how fast that booted? Does your Windows system boot that fast? Does your iPhone boot that fast? Does your iPhone even come out of sleep that fast? Watch again. Okay, here's me turning the power off. Well, actually not turning the power off. Resetting the CPU. Okay, here's it's booting the entire operating system from scratch. Could you even see? I don't think that I had it all the way out of the board before it had completely booted and started running the new operating system. So props to you, Pico Pi.
Blazingly fast.
Yeah, it's blazingly fast. Okay. So now let me go back here. Okay, there's one more thing I wanted to talk about before going into the conversation that I had with the microzig people, which is, okay, well, why Zig? Okay, why Zig? Because Rust has got this handled, and the answer right now is, well, maybe Rust is a better choice actually. But why not MicroPython? Why not TinyGo? Why not C? Why not C++? And I think the reason why not TinyGo is kind of purism on my part, plus a little bit of magic, plus it's got a garbage collector. It's not the one that's implemented in regular Go, but it's a garbage collector that is very small and uses simpler technologies, whatever. But it feels like it's a hack. Like, again, it seems to me TinyGo seems more like a toy project. Like, yeah, you could use TinyGo. It's probably useful for a lot of things. It's probably really fun as a hobbyist. Would you ship TinyGo? I mean, yeah, you probably could. It's production ready. There certainly are people shipping TinyGo, which is why the website exists and the businesses that are behind it. But I don't know. It's kind of a purism thing. I think I want to be at the metal. If I'm going to be at a microcontroller, I want to be at the metal. Why not C++ and C? Well, the C++ Arduino thing, it's kind of the same thing. It's like this shim. There's a whole bunch of magic. I don't know where everything is. Why not C++? I don't like C++. I don't like the complexity it brings in my life. I'm too stupid for C++. Why not C? This one, C is just a really obnoxious language to deal with. And there's still a lot of magic in C. As I was reading that blog article, I was learning about this magic that's going on in C that's like, okay, why can't I just write a function and get this thing working well? Turns out that depending on what you're using in C, C has a lot of globals at the linker level. It has a lot of things that it depends on that need to be inserted, and they have to be named, and they're not really documented. You can use tools like, ARM EABI object dump or something like that, and then you can get out what the symbols are, and you can see where the symbols are supposed to be located, and you can map that out. But it's not something that you can just know or easily. C's got its legacy. It's got history to it. It's not necessarily that these choices were made on purpose, but there's just a lot of stuff that's going on in C that makes it cumbersome to figure out how things are going to work, and not knowing what you're going to need to know. Why not Rust? Rust is something that I just had a lot of challenge in learning, and I just didn't get. I would totally do a microcontroller project in Rust. I think it's perfectly well suited for the task. I think that what you're going to do at the microcontroller layer, you're not going to be banging your head against the borrow checker every 5 seconds. If you're one of us lay people.
It took me like a dozen times of trying to start Rust and then giving up and then trying again before I finally got it in my head. It's not. It's a time investment. I feel like it's true.
Yeah, but I think the embedded Rust side at this point today, March 13th, 2025, I think Rust is actually a good choice for embedded in terms of what it offers, and the complexity that you have to deal with is relatively low. Because if you read the book Learning Rust, Rust is a really simple language up until the borrow checker and box types, and then
That's
it's
the whole point of it.
Well, no, but I mean, like the learning curve is like, this is easier than Python, and then this is the hardest thing I've ever encountered in my life. The learning curve is a straight cliff face, hard. But I think that Rust would be a better choice than Zig. But why Zig? And so Zig, one of the Zen of Zig things, let me see if I can bring up the Zen of Zig.
Type zigzag in your command line.
The way that this is working, let's see, if I do it on here, that would actually probably work for me pretty well. Let me see if I can bring this up.
Salon and improvement lab.
No.
I'd go there.
No, I'll do it this way.
Go to Pittsburgh.
All right, Zig Zen.
My salon is low level, free and open source.
Well,
Yeah.
no. Dealing with this TV is such a. Where did it go? Okay, there we go. Yeah, trying to. I actually have a better time if I can have the recording software up to watch the recording software rather than the TV because of the lag. It's just like it's off by 3/4 or like not 3/4, like 1/3 of a second, which is just in that like terrible zone. Okay, so memory is a resource. I think is a big one. Communicate intent precisely. Let's see, was there something else? I think there was another one. Reduce the amount one must remember. That's an important one.
Yeah.
And yeah, so the idea that Zig is, C is too high level. We need more memory control. That idea in Zig, I think, is what would and perhaps will make it perfect for microcontrollers. Because Zig itself is not doing a whole bunch of magic. It doesn't have a whole bunch of handshakes. Zig has a learning curve that's kind of like a little like 6-foot jump. It's not quite a step, but maybe it's not that bad even. But like there's a bit of there is like right at starting with Zig, there's things you have to learn that you've never encountered before, similar to Rust, but those things are in whole I think a lot simpler. The idea that you have to allocate memory every time you want to use it, and there is no allocation in the standard library, and there's no allocation like that you would be shunned as a non-believer, and you probably shouldn't use Zig if you're doing allocation inside of library code. without an explicit calling it with, no, you always have to pass an allocator. But this makes it simple.
It's a convention.
Yes.
You don't, in theory,
So-
have to pass an allocator.
So yeah, so if you don't pass an allocator, that's when we shun you.
Right.
Yeah.
But there were some cases, at least in Zig point 10, where there would be an allocator. Like you can set allocators at different levels. You can say, okay, everything I do with this whole library, I want it to use this allocator every time. Or you can have it at the layer where every time you call a function, it sets the allocator if it needs one. That's more what I was referring to. But the point being, because Zig doesn't have any hidden control flow, because it doesn't have any hidden memory allocation, because things are so explicit to a fault, it, I think, is going to make my microcontroller journey much, much simpler. Also because MicroZig is young, I think that there's a chance that, because there's only 10 board files in the repository and not 600, and the number of abstractions are relatively few. Although I will say, we hate Rust macros and C macros. Zig is doing it right, but I do think that a lot of people in the Zig community don't separate, because there's this line that doesn't exist or has never needed to exist before between macro and code generation. And Go went full all in on code generation with no macros, and it's a bit too much of a learning curve and kind of obnoxious. And Zig went too much into Zig. So Rust has a macro system, but it doesn't work with the code generation. You can't get the documentation. Zig might have gone a little bit too hard into the macro is the programming language system, because the metacode generation is intense, or can be. So that's one area where, if you're looking at Zig and getting into the microcontroller code, there's a JSON file that gets parsed that at comp time generates the code that you'll then be using. Now, you still have all the type information and everything for that, but it's a little bit weird that you pass something in as a string and then on the next line you get to use it as a function. So, like the code is generated as, it's a macro system, but it's like it's weird. Just like the borrow checker is weird in Rust, the macro system in Zig is beautiful and powerful, but I do fear that sometimes it seems to me like they lean too much into it because it is so powerful that you can just generate a bunch of crap and then. But at least you get the types. It's not like Rust where you don't have the documentation for it.
Why didn't they just run it separately and put it in a Zig file, import the Zig file?
I actually would like that approach. I think that sounds good. I think that that's a good way to delineate and say, okay, this is a generator file, blah, blah, blah. But I would like to see I would actually like to see the code. I would like to be able to see what got generated, because and this is my inexperience with Zig. I don't know how to navigate. Like in Go, I do Go vendor, and now I can see all the code. And if I need to make a little tweak, like I'm thinking I might need to submit a patch for this or a bug fix. I do Go vendor, I edit the vendor file, I run it again, I see that it works, then I go make the PR, right? Like my downtime or my ability to quickly iterate through something to figure out where bugs are and how something was done is very fast. I don't know if Zig has something like that. When you do a Zig fetch, I don't know where the source code goes. It doesn't seem to go in the local directory. It doesn't seem to go in the .cache Zig directory. I'm not sure where it is. Maybe once I find out where it is, I'll feel great about it.
Yeah, it goes in a global cache. I could probably show you. But.
I would love to see that, because that's one thing that I want to be able to do more quickly, is be able to. I'm glad, but it's like in source form, right? Like
yeah, it is.
GitHub.com/whatever, like navigable. Okay, because all I was seeing was hash files, and I was thinking, please tell me that it didn't just take like the commit hash and then turn that into a directory, and then like somewhere in one of these hash folders is.
If it was doing just the binary, you would know it, because I think you'd have to modify your build file for that.
Okay. Anyway, that's just something that I personally would like. I don't think it's the worst thing in the world to not have that. But so that's why I think Zig could be a really powerful choice. Is that there's more explicitness. And I think that people in the Zig community value not magic in the same way that people in Go community typically value not magic. I think there's less of this, pious, bro, you should use microzig. When I asked how would I do this without microzig in the microzig channel, I got a beautiful, friendly answer. Not like, well, dude, this is the whole reason microzig exists, so you don't have to do this crap. It was like, yeah, so if you want to do this without microzig, the first thing you need to do is run zig build verbose, and you'll see more of the steps. And the steps you need to look for are this and this. And once we kind of, went back and forth, and it was very friendly, and I really, really, really enjoyed that. Of course, the microzig community is very small, and all small communities are friendly, and all large communities are toxic. But, there's some hope here. So let me see if I can bring this thing up to show you, and then maybe we'll actually look at the code for 5 minutes. After all this, let me see. Where is my, where did it go? Here it is. Okay, there's that. Okay, let me go back to where I started and see if I can get this on this other screen here. Okay, it is not letting me move it to the other screen. That is weird.
I saw a rectangle like you almost had.
Oh,
Okay, there we go.
Hey. Oh.
Where is it?
Oh,
Oh, that's weird. It's full screening both. Okay, so, and then there was, all right, so this, so here's the exchange. Let me see if I can get this bigger so we can read it better. Can we get rid of the other crap? No, we can't. Okay, oopsies. Oh well. Yes, I just want to go over a little bit of my exchange here if I can find the part where I entered it. Okay, I think that was right before I came in. I think I came in, hello, newbie here, blah, 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 blah. All right, so I went through, I said, hey, I did what was on the website, it didn't work, I couldn't get the light to blink, what am I doing wrong? And it was just like super, super helpful. And then we came to this thing where, of course somebody read too fast because, before they even read my sentence, they responded with, it's because the GPIO is different. And like my second sentence was, I changed the GPIO. But that happens. That's everywhere. I expected to appreciate it. The person was super helpful. So sorry, I don't even mean to pick on him for that. It's just, one of those funny things that happens. Or not funny, annoying, or I don't know, whatever. It happened. But he was very helpful. They were all very helpful. So so the first thing was, okay, Pi website says these things are backwards compatible. Turns out, well, they're not exactly. One of the GPIOs is different. The most important one in this case for the Blinky program being the GPIO that blinks the LED. Okay? And you'll notice I'm not blinking the LED on the board. That's because the way this board is wired, you actually have to, there's another microcontroller on here, which is the Wi-Fi chip. And you have to communicate with the Wi-Fi chip and tell it to blink the LED because I guess it's expected that what you're going to use that LED for is
The Wi-Fi status.
yeah. So
I guess that kind of makes sense.
I don't know why they couldn't just put 2 LEDs.
Yeah.
But anyway,
They're expensive, okay? It's like a fifth of a cent for one of those things.
yeah. So I explained that I did this breadboard setup. Once I realized the GPIO was wrong, I did the breadboard setup, and got to have the resistor there because you know what I did when I didn't have the resistor. I saw a bright light and I heard pop, and I was like, okay, that resistor's not optional. It says in the data sheet to use a resistor. I was like, well, how much power could it be? Enough. Yeah. And then there was a little bit of confusion because on the website it says one thing and the repo it says another. So I'm looking like an idiot asking, where's Pico 2 ARM Blinky? Well, in the website it's called Pico Blinky, and then in the repo they've renamed it, and the website's not updated yet. And then let's see. So we got to make sure that we do release small because, of course, if we do a release fast, then that's not going to be able to fit on the microcontroller. We want as few instructions as possible.
Does that work with a plus in there?
I was assuming that this was the Zig 0.14 syntax because I tried. I don't think that worked for me. I assumed the plus was a typo, and it didn't work. And I added the plus, and it didn't work. And so I'm assuming that that's a Zig 14 way, not.
I'm on Zig 14. I think that's a typo.
Okay.
Yeah.
Well, just the whole thing, de-optimize equals release small. Is that?
So that's build exe versus, there's two different.
Oh,
yeah.
okay.
But it's not a 0.14 thing.
Okay, all right. So he was talking about something else then. All right, so where do we get to the important stuff here? All right, so he says, what version of MicroZig are you using? Well, the one that it says in the documentation, of course. Don't use that one.
Never use that one. That's old.
So anyway, but the point was, the thing that was messed up, I'm having a hard time with the glare reading these messages and seeing and like trying to scan where it was. But the thing that ended up being is I was using the wrong version of the SDK, because the Pico Pi and the Pico Pi 2 are similar. Almost all of the GPIOs are in the same physical layout, but there's different initialization for them and some other stuff that wasn't working. So even though I was able to get it to flash with the first binary I built, it flashed and then did nothing. So I was using the wrong version of MicroZig, and then I was using the wrong board file. I was using the Pico Pi board file. Turns out that you need to, or not board file, board configuration that generated the board file, I think might, or I don't know. The board was wrong. I needed to use the Pico Pi 2 board. And then there was, once we did, oh, boom, baby. Yeah, so once those two things, the GPIO, the board file, and the version that we're building with for the how, that's another thing I could have mentioned earlier. But your program is the kernel. The how are the drivers. So when you think about a Linux driver, that's all up to the operating system layer, down at the microcontroller layer, hardware abstraction layer, how. Basically, each how is a library that's a driver for a thing. And then, yeah, I want to encourage everybody to watch this. This is one of the things I wanted to mention earlier.
You could
everybody
turn
should
it
take a look
infinitely
at
and have
this talk, because it's much shorter and probably will give you more information than I did this entire night. But it's building an embedded ecosystem for my past self by Matt Knight. I believe that he is the person who started MicroZig, and he's at Tiger Beetle. So that was and this is still messed up where I have to switch between those for some reason. That's an aside, but that's one of the things I put up there with that linker script site. And then, okay, so then I'm asking, so how do I do this on my own? And then he's, and we're just going back and forth, kind of sharing ideas of like, how do we break this down into steps? And the good news is MicroZig I think it started out as a fork of Zig, or like it had to modify Zig or something like that. Because of something. I could be wrong about that. But MicroZig it's not messing with Zig. MicroZig is basically the collection of libraries that work for boards and devices, where devices like a rotary encoder, an LED in the simplest form, your simplest device is your light. Then you've got things like rotary encoders, you've got RGB LED displays, you've got your Wi-Fi, you've got your temperature sensors. So MicroZig is a repository that is collecting examples of how to use those devices with the MicroZig hardware abstraction layer. So there's still more that I want to learn. I would love to do a presentation like this again when I actually know what the heck I'm talking about, if that ever happens. There were a couple of tedious but unimportant things. Well, I mean, they're critically important, but they're not. It's not like you need to learn how to do. From my perspective, it's not something I feel like I need to learn to be productive and being able to fix bugs. Like one of them is the ELF to UF2. UF2 is a format that allows you to take your binary. Lots of microcontrollers do this now. It makes it much simpler. You push the reset button, you plug them in, the microcontroller has embedded code that emulates a USB drive. Whenever you copy a file over to it, I said something completely off base, huh?
No, it's funny that's how you got a USB driver, like it pretends to be USB, that's funny.
I mean, it is so much better than how you used to have to do it.
Yeah, so compared to the 3 different variations of ST-Link and OpenOCD and all that stuff, which you still have to use. But it's a method of flashing where the board itself has what it needs to be flashed. You plug it in, it appears as a USB drive, you drag the file over. If the file ends in .uf2, then it just writes it to the ROM on its own. So the microcontroller has that baked into itself. When you pull down a line on here, whether through a jumper or a button or whatever it is, you plug it in, it does this, and then that's how you flash it. So that's one of the things where that's still different for various microcontrollers, but they seem to be converging on this because I've noticed this with several things now, and I think that's great. When I was modding my GameCube most recently, I did some different mod to it. I think it was the GameCube. No, it was the Nintendo Switch.
How recent was this?
A month ago.
Okay. Because I read your old articles. I'm just wondering when you're talking about. That's all.
Oh, okay. Yeah. So no, I modded the Nintendo Switch, and actually I think it was using the same. I think it was using the same chip. Actually, that's probably why it was that way. And I do want to get into some actual code. I'm sorry we haven't done the actual code, but yeah. So I got to continue. I haven't read all these replies yet because they came while I was sleeping. Some of them, and I just haven't got around to it yet. But the point is, I had a good experience. I liked it. I appreciated the way that it went. I learned a lot. And I feel like from that exchange back and forth, like, yeah, Zig is the place for me with microcontrollers because I'm finally going to be able to understand enough that when I want to use something and there's no driver for it, that my belief, my hope, my faith is that I will actually be able to get to a point where I can write a driver for a rotary encoder that isn't already in there. Because that's one of the problems with microcontrollers, where it's like, okay, yeah, if you want to use the toy project with MicroPython, fine, but what about when I want to go on Alibaba and I want to get this other thing that is not part of the toy SDK and I want to try to, I need to figure out how to program it for real. And if I'm sticking with the Arduino and the MicroPython stuff, I can only work at that layer of abstraction, and when I need to do something else, like, oh well, So
You hope someone else already wrote it.
yeah, exactly.
Yeah.
And I'm a programmer. If I need to do something on a microcontroller, I want to know, I want to have the confidence I can do it, and that's why Zig, the biggest reason of all. Anyway, so with that, that's the end of well, I guess we need to show the code, and then I want to take some time to actually tinker with the code to do a little bit more. But that's kind of all the high level material, and most of it is. You just have to understand how a microcontroller works. All right, let's see. I called it Zico Blinky. Let's see if we can get this.
That's like the biggest thing that I've done some microcontrollers like GoBot with Go, and they have a ton of drivers. I wrote some drivers. That's like the thing that we have with just regular programming, like foreign function interface. Right? It's like I need some cool function from another language, and I want to use it in my language, right? And it's the same thing with the drivers. It's like you'll see that there are Python drivers out there for microcontrollers, there's Go drivers, there's C drivers. It's like it would be nice if we could just converge on write some driver code, and then you can plug it on any other platform you want, right? Because it's like most of the driver code is doing the same exact stuff, right? And that's the thing, most of your hardware devices on microcontrollers, it's memory mapped, right? So it's just a memory address that you're saying, I'm going to go here, I'm going to write some bytes here, I'm going to read some bytes from that, and it's not crazy, but and that's kind of how most drivers work, but it stinks that you have to kind of reuse that or rewrite that code to a new language every time you want to use it, because there is nothing out there that's like, hey, write generic drivers that work for any platform, right? Because we're not, GoBot and GoCV are trying to do that in some way where they're trying to make that more portable, but it's funny, a lot of people are still trying to do something like that.
So I don't know about MicroPython, but Python lets you directly include C code.
That's cool.
So I wonder if there is a way for MicroPython to do the same. Even regular Python, it's fairly easy to interface with C code.
Well, the material that I want to see that doesn't yet exist would be, the getting started would not be, okay, here's your toy project in MicroPython. The getting started would be, here's how to use this toolchain, Zig, because Zig seems like it's going to be a lot simpler. Here's how to use this toolchain. You're going to get your Hello World style program where it's going to fill out the RAM, it's going to fill out the ROM, it's going to fill out the stack, it's going to wipe the heap, it's going to set the initialization vector for the timer and one other interrupt. Some of your interrupts are timers, so you can tell the microcontroller, hey, when the clock has done this many cycles, hit me back, and that's how you do a sleep. Well, that's one way to do a sleep.
Where it's like if something's taking too long, you can basically say, hey, you're taking too long, I'm going to reset and start back over.
Yeah. So you've got interrupt controllers like that. So like one or two interrupt controllers, And then here's how we take something like a rotary encoder or an RGB display or something like really simple. And you're going to do the whole thing without a how, and you're not going to do it the stupid way of, okay, we're just going to literally no-op for, we're going to write a loop of no-ops. No, we're going to use the interrupt. The interrupt's going to call a function when the timer's done. And we're going to use the interrupt's going to fire when the button's done. But like something really simple like that, that's the hello world that I really, really want. I feel like if I get to that point, then the world's my oyster, because if I can do that, I know how to do linker, I know how to set the interrupt, I know how to handle the interrupt, I know how to write the driver for the rotary encoder. Well, then if I need to figure out how to write the driver for the touch e-ink display, I could do that too. Or if I need to write the driver for the Wi-Fi, I can do that too. Because I think the driver for the Wi-Fi is simple, and that I don't think that I'm going to have to do anything with AES or rotation of keys, or I think that basically it's like a serial interface where you say, like in the old modem days, like here's the password, new line, carriage return, something. Here's the
there's two options with that thing. You can do that, which is like you can just say like, yep, set it up, and it has like its own little AT commands, right?
AT, that's what it is. AT commands.
Like, yeah, do this and do that. And that works pretty good, but if you want to do better performance, you can go past that and go lower and say, no, I'm going to call some libraries and do the thing myself. And that gets a little crazy because it is more fun and exciting. But you're doing that because you want more performance. The AT commands can get you pretty far. But if you want this thing to actually move stuff around.
So, but the AT commands, those are those typically on the microcontroller themselves?
Yes, so that's the thing is you can run the ESP32 in that AT mode, or you can just be like, okay, just run it, and I'm going to listen. Like you can basically have like another microcontroller drive it and tell it what to do.
Yeah. So yeah, what I just need to be able to handle the Wi-Fi. And there were some comments that, sorry, I didn't see the comments because I was flipping between screens, and since I'm both presenter and person running the comments, I wasn't looking at them. Red Hot Chili Peppers reference, maybe, I don't know, I probably did make a Red Hot Chili Peppers reference, but I did it subconsciously, not intentionally, just because I happen to listen to a lot of Red Hot Chili Peppers. If you use ZLS to go to definition, takes you to the file of dependencies. Sadly, MicroZig uses too much comp time, and ZLS works poorly. Okay, yes. So then I feel validated in what I said earlier, is that I think I understand why there's so much comp time, because there's also board files, a third overloaded definition of board file. There's a board file that describes the board in a hardware language, and you can take that and read it kind of like JSON or XML, and then some of them actually are in XML, and then you can spit out the code. So you can do that. So this person whose name I can't pronounce is saying that. Okay. Plus was definitely not something about 0.14. Okay, so we'll take a quick look at the code. The code's not that interesting. I just copied and pasted it off the website and made one or two modifications. So we've got our build.zig. This was completely copy pasted. Let me see if I can get it on the screen a little better or something here. So we're importing standard. We're importing microzig because we are doing the build file. We can use standard. We are setting the family of chip to be the RP2XXX6, which is going to be PicoPi chips.
Are you implying you couldn't use standard outside of the build?
You can do it in the code that's going to be running on microchip.
I guess we should be able to.
Well, there's no platform code on the microcontroller that it can call though, so you couldn't include the standard library, at least not all of the standard library, because a lot of it requires system calls.
So the reason that I was saying that is exactly the reason that Zig exists, because typically, and that's why you called it out.
Yeah, I'm like, the whole point is you can run the standard library on the microcontroller.
Yes, that is one of the tenets of Zig, is that, normally you can't run the standard library in any language on a microcontroller, be it Rust or C or whatever, because of all that hidden initialization that happens, where memory is being allocated and moved around. And the standard library has specific symbols that are meant to be referenced in a way. There's certain global variables that are meant to be initialized a certain way, and that happens at the operating system layer pretty much automatically in terms of your way you interact with the toolchain. In Zig, because none of that's happening, you actually can use the standard library because it doesn't require hidden initialization. So,
You couldn't use all of it though. Because
right.
You could use some of it.
If it's the Linux or Windows specific stuff, then right, you have to have that operating system use as well.
Well, and you might have to have like some sort of custom allocator if you needed to use an allocator for some part of the standard library, but yeah, it is more open to you. Anyway, this is what I wanted to get to. This line right here, little mistake. And the reason is Pico was only an ARM device. Pico 2 can run either as ARM or RISC-V. RISC-V. It would be shown here as RISC-V if it was supported. I don't know if it is. But that's really interesting too. I still want to learn more about RISC-V, but it seems that that RISC technology has come such a long way that the RISC-V open source hardware, ARM has been so stable for so long. Yes, they introduce new things all the time, but basically the way that, and I hope that I'm not saying this in an offensive way, but basically the way that ARM has pioneered the space and made it so accessible, and then kind of slowing down to some extent, kind of like, Internet Explorer 6 slowing down gave room for Firefox to become a thing. And it seems that ARM, having reached a certain level of acceptance in the market and kind of forcing the knowledge of RISC upon people, in my hypothesis, which may be completely wrong, but seems to be giving way for RISC-V to take shape. And I think that's really awesome. I think that the idea of having more of these microcontrollers on fully open hardware is an awesome idea. So that's one of the things you can do there, side note. And it seems that I noticed a lot of YouTubers are talking about RISC-V when I was looking for microcontrollers, and that did not happen a few years ago. So I think that there is a shift in the industry right now where there is room for the open to thrive. And that's going to be a lot more helpful with things like this, because one of the reasons all the proprietary tool chains, blah, 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 is because the proprietary microcontrollers need proprietary tool chains. If we have an open microcontroller system, then we, again, don't have to deal with all of that, abstract all the things. Okay, so that was basically the only thing in here. You can see this build file is super, super small. We're giving it the name Blinky. We're selecting the board that we're going to run on, the type of optimization we need, which is going to be small, and then where we're going to start from, and that's it. That's the build file. And that, for those of you that are not as familiar with Zig, that replaces something like a make file or a rake file or CMake or whatever. The build file is written in Zig, and that gives it a lot of advantages because it can do any of the comp time. I don't want to say introspection because that's not the right word, but because of comp time, for those of you that don't know, because some of you are not actually Zigites at all, or Ziggers or Zigglers or Ziguanas at all. And I mentioned this a few times implicitly without explicitly stating it. Zig is the scripting language for Zig. It is the macro language for Zig. It is the build language for Zig. It is the programming language for Zig. Can become a little bit confusing because sometimes you don't know which Zig you're using except by context, but the files are usually named in a way that you can tell when you're using which. Zig is also the object notation for Zig, which we'll see momentarily. So then in the build.zon file, Zon is Zig object notation. Here is, I did a Zig fetch save, and I got main, and then you can see here that it appended the current commit of main to it, and then gave with the hashes. So that's what it needed there, and there's not really much else in here. The name of the project, the version of the project, paths for stuff.
You're not on 0.14 yet?
I can't use 0.14 for microzig
Okay.
yet. Microzig is still 0.13. Unless I did something, no, it didn't.
They said they were working on a release in your Discord messages you showed.
Yeah. And then the last thing is just the main.zig. The main.zig is very simple, and I'll try to show you how this is working. So here we go. Microzig again is the how. It's the collection of drivers. That's what it is. And it is also the comp time code that generates essentially drivers on the fly. So
At compile time.
yes.
Fly up at compile time, not like at runtime.
Well, yes. Sorry. Yes. It is. It's not. Yes, it's not generating them at runtime. It's generating them at comp time. So okay. So here we have. It's called pin config, and this is just what it sounds like. I'm just configuring GPIOs, and so I'm only configuring one. But this basically right here is kind of, in a way, it's kind of returning a driver. Like I'm passing in some stuff, telling it how I want it could be configured. When I run the compile step, it's checking that against other code and then eventually spitting out the object that does the things that it needs to do. So when we look at, I'm going to get the pins here, and this is comp time 2, as you can see, because it's outside of main. Now, the init function is being built by Microzig, but there is a way to look at that. I haven't got that far to show it. I wish I had. I'd love to show it. That's going to be one of my next steps. And then I'm just toggling the pin, and then I'm doing a sleep, and I'm toggling the pin again. So what this is doing is, I believe that this is using an interrupt. I don't think that this is counting no-op cycles. That's the way that they typically show you in your hello world, is you count no-op cycles and you call it sleep. But there's also a timer with an interrupt. And being that they've said that this is the best supported and that timers are one of the first things that you create, I'm pretty sure that this is using a timer. And
We could check the assembly.
we could. And then, yeah, so it's just toggling. So that's all it's doing. And then it's very, very simple to build. It's just Zig build. There's no special thing that you need to do that you wouldn't normally need to do. And I could probably run Zig clear cache or something. Do you know that off the top of your head? Is it Zig clear? Oh, it's just Zig out?
Yeah, Zig out.
Okay. So then,
Or is your Zig cache actually give a separate folder for it, I think.
all right, let's see. I don't think there was a cache folder here.
Zig, yeah.
Oh, Zig cache. Okay. All right. So we'll let it take a long time to do this. And we'll do, whoops, not version. Oops, let's get rid of it again. We're going to do, I meant to say verbose. And I don't know if that's going to do anything. He told me to do verbose, and I didn't try it yet. Okay, cool. So it's spitting out some stuff. Can I get it to not do all of the CLI of this? Anyway, so it's building stuff for itself. It's building stuff for the build system. It's building stuff for the build files, and then the last step is that it builds the code.
That's why it's doing SQLite right now. And I was like, wow, on that thing.
Yeah. So that's one thing that's a little confusing. Like I said, the build system is a scripting language that is not a scripting language because it's the compile language, and it compiles when it compiles and generates the code.
Yeah, I didn't know that SQLite was used. Is that just Microzig, or?
I don't know what's using SQLite. It might be something in the standard library. Yeah. I would imagine it would be something in the standard library if it's, well, it has a good standard library, and
Yeah, I mean,
SQLite is something to include in a standard library. I think it makes sense, but I don't know. Anyway, so I'm going to have to break this down and look at it at a size that actually makes sense. But one of the things here is freestanding. And I think freestanding is a reference to does not belong to an operating system.
yeah.
So it's something that you would use. I think that's a convention used in other tool chains as well. So we can see here, this is the command that Zig build ran a bunch of macro stuff that ultimately ended up running. And I don't know if I can get all the way down to the bottom of it, but this is something I'm going to have to dissect and cut down line by line and try to understand what it is. But we can see here it's specifying the type of CPU it's using. It's specifying a dependency. It's specifying some cache files that I'm guessing it built before. Is that what that is? Or I'm not really sure.
Yes.
But anyway, we can actually see what's going on in a reasonable way.
And you can see where your cached files are too. That's where it is on your system. So if you go into that user/aj/.cache/zig/p, and then in those folders.
Okay, but this is what I was talking about. This is what scares me. This is like big hash. I was expecting like a a source tree looking thing. But yeah, knowing that it's there is good.
Yeah, you have a zig file, so it is source code.
Yeah, so that's probably the commit hash. So I guess maybe P, I don't know what P means, but maybe P is where the source code is. Because I looked in one other file at random and it was not source code. Or I didn't think it was.
Yeah, there's different things in the hashes.
Yeah, 'cause a lot of systems, they just use a letter because it's part of a hashing system or something. Anyway, so in Zig out, we have firmware. And then under firmware, we have Blinky. And then I'm actually kind of interested to see. And then we have the Blinky thing wrapped. So this is 605 kilobytes, which that seems like a lot, but I'm guessing that includes, I don't know. I'll have to learn about it. But what you can see is the actual file that goes on the device is 4 kilobytes.
Oh wow, that's incredible. Do LDD on Blinky.l. I'm just curious, but what? It shouldn't have anything. It should all be there.
All right, LDD. I don't have LDD.
He's not using Linux, he's using Mac.
Ah, okay. Never mind.
Well, wait, is it like dilib something?
Something-
I've done this once before. I don't remember. But
That's
yeah.
fine. No, but that's
It looks like the smooth frame thing just turned on for the TV. Like it's like tweening the box like as you're typing. Yeah, do you see that?
Yeah. Yeah, it's weird.
It's funny how.
So object dump, isn't this one of the ones I can use?
Yeah.
Do that, maybe? Is that?
That's a very slow object.
You might have to specify the architecture if it's for a different one than your
If it's
on.
ARM, yeah.
Well, yeah, you're both on ARM, but one of them is what, ARM 32?
Well, since I don't know that, I probably won't. Oh, yes. Okay, good news. Good news. Situation's better now. In 0.14, its package name is part of the path. So
Oh yeah.
that's why you were telling me one thing, and then it didn't seem to be true because you were living on the edge of the future.
Yeah.
All right. Yeah. So anyway, that's like I said, it's not really much about Zig. Sorry. But hopefully, I mean, my hope is that for some people in the room, it gives you some of the missing pieces, some of the missing vocabulary, so that when you go to attack that microcontroller project, hopefully we can get to a point where we can write drivers. Because when you're writing drivers, that's when you're actually an embedded developer. When you're doing MicroPython and Arduino, and you have to buy a branded device that's guaranteed compatible with the board you got. And I don't mean this in a demeaning way, but you're not an embedded developer. You're an embedded developer when you can get something off of Alibaba, GPT the Chinese out of it, and connect the wires together and write a driver.
I only get a good spec sheet out of it, 'cause that's the biggest thing. That's the biggest thing when anytime you're doing government is you want good specifications. Like I want to know what the addresses are, what registers are, like some of their timing. Like there's just a lot of hardware that you have to know what it's doing, how to set it up. A lot of that is nicely documentation documents that you have to go through and just parse through them and start hacking away some code.
Yeah, and there's good data, and sometimes the data sheets have bugs in them, and that's its own. Yeah. But one last thing, and note of this. So another thing that I didn't realize is that you're not supposed to just buy one of these. You're supposed to buy 2 of them. And the reason is they come with this little debug header board. And you need a device to act as your debugger. So you can either buy a debugger for however much that costs, or you can buy another one of the Pico Pis, connect its GPIs to the debugger line, and flash it with the program that makes it the debugger. So I'll have to buy another one and flash it with the program that makes it the debugger, so that I can then plug it in as USB and then open up a program on my computer that will then allow me to debug the code. Because you can get print lines in the debugger, but unless you're doing Morse code and you've already gotten far enough to get the light blinking in the first place, which is sometimes a challenge if the website says that it's backward compatible, but it turns out you need a different board file and the GPI is different and the version on the website isn't the version that works with that board file. You know, you need you need a debugger to be able to figure out why you haven't even got to the blinky light, and preferably to not have to use the blinky light as Morse code. Although you've got a lot of GPIOs, so put up a red one, put up a blue one, put up a green one, put up an ultraviolet one. The one that gives you cancer is the one for your critical errors. Then you go from there. And then the blue if you got an email on it or something, or the Wi-Fi's connected. Anyway, so yeah, that's what I got. I sincerely hope that is helpful and shed some light in some areas where you've been sitting in darkness, and may we connect again and work on some project together. Also, I'm going to show you real quick. I have, I work from home out of a shed, and let's see if I can get this on here. Just doing a quick plug for the ONeal co-working space. If anybody wants to join in on the ONeal co-working space, I would love to have some. And of course, the little thing on the phone that syncs the videos and then deletes them after a day has already run, but that's okay. I've got some pictures on here that will serve. If I can. Okay. All right, here we go. All right, so this. Oops, now I gotta deal with that too. Okay, so this is the ONeal co-working space here. You can see we've got highest quality R15 insulation. So if you'd like to get, if you didn't get cancer from asbestos and you'd like some other options, remember R15 is also used in rat poison, so it's certainly a good option for you. And then there's the little desk. There's the little desk. There's the big desk, which that's got some soldering equipment and some other stuff on it right now, but that's a full-size desk. This thing, believe it or not, turns sideways. The picture, aspect ratio makes it look like there's not a lot of room, but there's plenty of room there. And then also, if you get frustrated and you just need a little nature, there's some plants, there's some shrimp, there's some seaweed and fish.
Little snack.
Yeah, and the desk. It doesn't have to be so messy. If I was going to advertise it, but anyway, yeah. If anybody's working remote and you wanna hang together, I will. I don't. No, actually, there's a chair. There's two chairs. There's one that you can't see. That's a fold-up chair right there. But there's another chair that's a nice chair like this. Well, it's not as nice as this, because my wife has the one that's just as nice. But there's another chair that's right here. So there's a second chair. Anyway. But if anybody's interested in working on a project together, you want to spend a weekend, like do some microcontroller stuff. You just want to hang out and do some work. Working solo is awesome sometimes, but I'd actually really enjoy having a little bit of company. So if anybody's interested in that, I'd love to accommodate this space and make it more suitable for somebody to come hang out and work once in a while or whatever. I'm a little south of Provo, so if that is of interest. And I'm gonna actually end the stream now too. So bye, people online. Thanks for joining in. Thanks for the helpful comments. And the hurtful ones. Actually, there were no hurtful comments yet. I'll get those later. Niles' friends are going to chime in. Like, why isn't this Niles?
Yeah.
Who's that guy sipping on the Pepsi? Why didn't the presenter have slides?
I love our comments.